Welcome back to our course on fluorescence spectroscopy, principles and biomedical applications. Glad to see you back. Today we're going to start talking about anisotropy. Actually, I like anisotropy because it can all be explained by chemical and physical principles. So let's start off by showing you what anisotropy is. So most fluorophores, even though they're randomly distributed in solution, they have defined transition moments. That is, they absorb light that is polarized along particular directions. DPH is sort of the starting molecule everyone uses to discuss anisotropy. It has absorption and emission moments along the long axis, which means the charge distributions occur along the long axis. And it's these, well, they're parallel in this case. These are really the origins of fluorescence anisotropy. Some molecules have more complex structures and more than one emission moment, and this introduces some complexity into the theory and into the results. And even to this day, some ambiguity remains, but we won't worry about that, at least for the moment. So let's first look at the measurement of anisotropy. Basically, you start with your normal square cuvette, and you have your light sources, but in this case, you have polarizers, which are in the excitation and the emission beams. And in one case, you would excite the sample with polarized light, and then you look at the emission, and you look at the emission parallel and perpendicular to the incident light, and you use those values to calculate the anisotropy, the differences in the sums what are used, or in other cases, we'll see the more appropriate case is the differences plus a slightly different expression for the sums. Nice thing about anisotropies, they're absolute values and they are transferable between laboratories. So in fluorescence, where you can't really transfer spectra between labs or intensities, anisotropies or intensity ratios are transferable, just like lifetimes are transferable. So let's look at the different definitions of anisotropies. There's two of them. One is historically used. The other one is more theoretically correct. First of all, what happens when you excite a sample with polarized light? Well, you're actually starting with a completely isotropic sample. The fluorophores are oriented in all directions. But when you excite the sample, we're now talking about a molecule like DPH with parallel transition moments, you cannot get a perfectly aligned sample. You get a distribution of angles along symmetrical around the z-axis, and these we'll see in a moment follow a cosine squared distribution. Well, the intensities along the axis and across the axis defines the polarization, the difference over the sum, or the anisotropy, which is the difference of the parallel and perpendicular over the sum of parallel plus 2i perpendicular. They can be interchanged with one another because there's no different information in the two, except that the formalism is much nicer in terms of anisotropy. This is sort of interesting. I'm going to emphasize this again. The polarized light actually induces a more ordered region in an otherwise homogeneous sample. Normally, if you want to do an experiment in an ordered system, It's something like stretched polyethylene. You get all the molecules to line up along with the polymer, and you don't give them any opportunity to rotate. And that, of course, gives you a anisotropic distribution and anisotropy. But that's not what we're talking about here. Here, the anisotropy is a transient one. It's introduced by the polarized light field, and it's only a subpopulation of the molecules that are ever excited. This is true in just about all fluorescence experiments, unless you use enormous intensities of light. And the orientation is not caused by the high intensity light fields polarized along the z direction. The intensity is because of the cosine squared probability of absorption. Fluorophores oriented in every possible direction, and this is what you wind up with when you have that cosine squared weighting of the absorption. Z-polarized excitation cannot give you a completely oriented set of DPH molecules. In the subsequent lecture, we're going to talk about what happens when you have a single DPH molecule in an axis. But as far as we're concerned, that can never happen, even if they have parallel transition moments. This is what you wind up with. And the orientation is due to the cosine squared probability, where the angle goes from the z-axis. So when the angle is 0, the anisotropy is 1. Well, the cosine is 1. And if they're perpendicular, the cosine is 0. There's no intensity along that axis. This is an important point, and it's often a point of confusion. What I just showed you was the distribution of the excited state molecule, or the distribution of their transition moments subject to vertically polarized excitation. This is completely different from the emission of these molecules, because the emission from a single fluorophore is more like a torus. It does not have that figure 8 configuration. The molecule is radiating out perpendicular to the transition moment in all directions around the z-axis. So you should not confuse the barbell structure I showed you previously, which is the excitation-induced pattern, with the emission that occurs from a particular dipole, which occurs in all directions. And I thought I could make this a little more clear because this would happen historically. Historically, when fluorescence was first looked at by Jablonski and those guys, they weren't really thinking about this torus, and they were thinking of fluorescence like a beam of light. And a beam of light is properly characterized by the intensities along the two axes perpendicular to the direction of travel. So that's the right definition. But when you get to this torus, it has components along emission components along the x, y, and z axis. So in order to properly characterize the total emission from this, you have to sum up those components, which happens to be that term I discussed previously, I parallel plus 2I perpendicular, one parallel directions, two perpendicular directions, and hence we come up with the definition of anisotropy. And all of the equations for fluorescence look simpler when expressed in anisotropy units. I guess I'll give you an example here. Uh, so here we have two hypothetical molecules. We have a tryptophan molecule and a human serum albumin. We've assigned them both a lifetime of 3 nanoseconds, and we know from other experiments what their rotational correlation times are. The tryptophan itself is very fast, like 50 picoseconds, and the serum albumin is much slower. It's more like 40 nanoseconds. If we wanted to describe the polarization of the mixture, we would have to use this equation. This 1 over P minus 1 over 3 to the inverse of that. It's a pretty complex looking formula to calculate the anisotropy resulting from these two different molecules. But if you wanted to do it in terms of anisotropy units, it's extremely simple. The anisotropy that you observe is equal to the sum of the fractional intensities and the anisotropies of each component. So you get the fractional intensity from this one, fractional intensity from this one, the anisotropy from each, and you add them together. And I think it's generally true in science, maybe it's not generally true, but in my experience it is, that the more simple the expression, the higher probability it is that it's correct formulation. I thought it might be good to just give an example of what these different sizes do to the polarization. We'll be describing a little later exactly how to calculate the anisotropy from the rotational correlation times theta from the lifetimes tau, but I thought I'd do this just quickly here. So if we have tryptophan and we use the ratio of the lifetime to the correlation time, you'll find that the anisotropy is very low. So 0.0049. Before this molecule has emitted, it has rotated many times, and the anisotropy is getting close to 0. That's not true with the serum albumin molecule, where the rotation is slow. And if you take the correlation times, plug them into this equation, you'll find that the anisotropy is around 0.28. And for both of these cases, the fundamental anisotropy, which is the anisotropy with no motion of the fluorophore at all, is around 0.3. So you see that for a molecule like tryptophan, free in solution, its anisotropy is 0. Bound to a protein or anything else, it can have an anisotropy near its fundamental anisotropy. Why do we like anisotropy measurements? We like them because they provide information on rotational diffusion. And that's about how it's used all the time, but that can give you a lot of interesting biochemical results. So anisotropy depends on the rate of diffusion. If the rate of diffusion is very fast, it basically before the molecules emit, they have randomized, and the emission is occurring in all directions. So the anisotropy that you see is very slow. If the solution is frozen, what you can do with things like glycol water mixtures, freeze it, turns it into solid glass. Fluorophores don't move. The emission is polarized because the fluorophores have not been able to rotate during the lifetime of the excited state. The other types of experiments that are very frequently done are protein binding experiments, one protein binding to another. As that happens, the rotating species becomes larger. I'm assuming the fluorophore is just on one of those species. And when that happens, the anisotropy goes up. So you can get a calibration curve and measure the binding constant and the limits or the stoichiometry of the binding. A similar thing is true with phospholipid membranes. Saturated phospholipid membranes tend to be in a solid state. Unsaturated ones are more in a liquid state. And a DPH molecule has a much easier time rotating in the unsaturated phospholipids than in the saturated phospholipids. So the anisotropy becomes higher, which I put here as the higher percent of saturated fatty acids that you consume, the higher anisotropy of your blood vessels, presumably. Here's a use of anisotropy that it just shows how useful it is for measuring protein association. Here we chose proteins so everything's in our favor. We chose melatonin, which we described before as being able to form a quadruplex, but that's not what's happening here. Melatonin will bind to the surface of calmodulin, and when it does, it rotates much more slowly. It also forms that alpha helical shape, but that's not important at this moment. So melatonin bound to calmodulin, which is increasing the concentration here, results in an increasing anisotropy, and from that you can calculate the binding constants of the binding affinities. Anisotropy measurements tend to be very, very accurate, and a nice thing about it, almost any association constant of two reasonably sized molecules is going to change the rotational correlation time, so it's going to give you a change in the observed anisotropy. Here's another case that's sort of quantitative. I chose this because it had very sharp binding. I don't have any idea why the myosin light chain kinase likes to bind to calmodulin, but it happens to be something that it does. And also the tryptophan residue is in the myosin light chain kinase, not in the calmodulin, which doesn't have any. And when the smaller peptide binds to calmodulin, it shows a blue shift, showing it's shielded from the water. What's very nice about this experiment is that the binding constant is so high that the binding is essentially stoichiometric. So as you add calmodulin to your solution of MLCK, it just increases and then it stops. So that's the stoichiometry of the binding. You can't tell the binding constant in this case because everything is bound, but there are expressions that we could use the data, like in the previous slide, where binding might not have been as strong. There are equations where you can calculate the fractional bound from the beginning and ending anisotropies. Again, it's easier than using polarization. And if they're both this is at the isomissive point. This was really tricky. They could use this easy equation because they measured the anisotropy right here. If you're measuring the anisotropy at any other point in this type, along this wavelength scale, well, the two species don't have equal contributions to the total intensity, so you have to correct for that, which is this more complex equation down here, which corrects for the difference intensity of the free MLCK and the bound MLCK. G factor. Everyone is always sort of confused about this. You know, what is the G factor in calculating the anisotropy? The G factor is basically a correction for the transmission efficiencies of the parallel and the perpendicular components on the emission side of the experiment. So here we're exciting with vertically excited light, and we're trying to measure parallel and perpendicular in intensity. That light might be going through a monochromator, in which case we've shown in previous lectures that the monochromator efficiencies can depend very much on the polarization. So that would distort the measurements, and these two experiments back here would be meaningless because of the bias introduced by the monochromator. By the way, the first letter is meant to be the excitation side. The second letter is meant to be the emission side. This is easily taken care of in this type of experiment, which we call an L format, because there's just one side to the experiment. If you change the excitation polarization to horizontal, well, it's like looking down on this shape here from the side, and the parallel and perpendicular are expected to be equal. So for the G factor measurement, you change your polarization to horizontal, and you measure the two intensities. You get two different intensities, and they tell you that there's a different sensitivity to polarization, the polarized light in the two different directions, and you can use that to correct for the two measurements you made, so you have a slightly different expression for the anisotropy, but this factor here, this G factor, is only correcting for the light of different polarizations, may not go through the monochromator with the same efficiency. This is still used, but not quite as much. Oh, another thing I wanted to mention, some of the new modern instruments will just do the G factor for you, and you don't even know that it's happening. I find that sort of dangerous because I don't trust anything that's automatic, I guess. But you can also do polarization measurements in a T format, in which you have a detector on each side. So the principle is exactly the same. You excite with vertically polarized light. You look at the emission on the two directions, parallel and perpendicular. You get slightly different answers, and you consider that to be essentially the G factor. So I'll back up here. First, you excite with horizontally polarized light. You get essentially a G factor for your T configuration, and you apply that when you do the excitation vertically. This method was used primarily when the incident light was not as stable as they are now, and it had values. It was valuable in correcting for intensity values in the incident light. Let's look at a biomedical application. We'll look at this a number of different times in different formats. So this is the microviscosity of cell membranes. That term has gone out of fashion because we pretty much realized that the microviscosity doesn't really mean anything. But in any event, there was an attempt to measure those microanisotropies, so microviscosities. So what was done is calibration curves were prepared of different fluorophores and solutions of different viscosities, and the assumption would be made that an anisotropy measurement here was equivalent to a certain anisotropy. So this was applied to membranes, and this was a very interesting time because people were looking at membrane structure and then protein rafts and things forming in the membranes. But if you have completely pure membranes, we have dipalmitoyl phosphatidylcholine here, has a transition temperature around 39 degrees, and it's just amazing when you're doing your measurements. The anisotropy just plummets when you go through the phase transition point, just like melting an ice cube. if you put cholesterol in there when you're making the vesicles, that smears out the phase transition. So the anisotropy can go either up or down when you're inserting it into a membrane, depending on what the where you are in the temperature range, or stated another way, you could say that the cholesterol sort of eliminates the phase transition. But anyway, this has been a very useful way at looking at the dynamics of membranes. Well, we'd like to continue with another example of anisotropy measurements. This one is pretty cool, I think. This is the unwinding of DNA by helicase. So basically, in order to replicate DNA, you have to unwind it, of course. And this is powered by ATP. So it zips along and it unwinds it. How can you detect this? Or at least how can you detect it by anisotropy? And the way it was done is they used 2 strands of DNA, and I forgot which one has the fluorescein on it, but it doesn't matter. One of the fluoresceins has it on there. And when the strand is not bound to the other complementary strand, it's a low polarization. When the strand is bound to the complementary strand, the polarization is high. So we know it's bound to the helicase, and it's not really doing anything, it's just sitting there, but that's because we need some ATPase to catalyze it, or ATP. So you add a little bit of ATP and zap, it gets immediately changed into single-stranded form, and the anisotropy drops way down. This is one of the neatest examples of anisotropy measurements. These are anisotropy measurements to look at the binding of the trip repressor protein. That's the protein that represses biosynthesis of tryptophan if the organism has enough tryptophan. And the trip repressor protein binds to this fragment of DNA, which was fluorescein labeled. So what was looked at here was how is the dimerization of the trip repressor protein related to the tryptophan content. And I've always thought this seemed to be presented in reverse order, but it's really not, it just seems that way. In the absence of tryptophan, you can see that the anisotropy of the labeled DNA is low. So basically the trip repressor would be active, it would not be bound to the DNA, and tryptophan synthesis would be going on. If you add some tryptophan to it, you find the anisotropy of that DNA fragment goes up, and that indicates there's binding of the DNA fragment to the DNA induced by tryptophan in a solution. So we have this spelled out here. The tryptophan causes it to bind to the operon DNA. And what's interesting about this is that even though it's not explicitly analyzed in the paper, it's clear that you can begin to see even additional binding modes of the trip repressor protein. So the anisotropy keeps going up, which would indicate higher aggregations of the trip repressor protein on the DNA. Okay, now we're going to switch our attention to time-resolved anisotropy decays. Of course, we always feel there's more information in the time-resolved decays. Until you know better, we expect the anisotropy decay to be a single exponential, and phi here is the correlation time, and there's a time, and this is the steady state version of that equation. So the rotation, the important thing is that the rotational correlation time depends on the size and the shape of the protein. And this is just to remind you why we use anisotropy instead of tryptophan, because if you have just a light beam, you can define its polarization by looking at it through a polarizer, but the radiating dipole has fields in all directions, so the correct expression to represent the total intensity is I parallel plus 2I perpendicular, rather than just the sum down here. So what happens when we measure anisotropy decays? So we have this hypothetical monomer, which is in equilibrium with a dimer. Let's assume we know, let's assume we know the correlation times. The monomer has a 5 nanosecond assumed correlation time. That means this value here, phi, is 5 nanoseconds. We have the tetramer with a 20 nanosecond correlation time. And if we were doing a biophysical experiment on this, we could determine the fraction which is in the monomeric or the tetrameric state by the intensity decay. Because if it's partially tetrameric and partially monomeric, we would have a 4 nanosecond and a 20 nanosecond component in the anisotropy decay. A nice thing about anisotropies is that they're very sensitive to the size of the protein. You notice here it goes up by a factor of 4 when the molecular weight goes up by a factor of 4. That's not the case. This is now for rotational diffusion. That's not the case for rotational diffusion, which depends much more weakly on molecular weight, or stated in our favor, the correlation time is very sensitive to the molecular weight. And here's just some typical molecular weights and correlation times of proteins, ranging from apomyoglobin and trypsin in the 20 kilodalton range, and going all the way up to cerebralbumin in the 66 kilodalton range. One of the things that is routinely observed, I lift the observed correlation times here, is the observed correlation times are just about always longer than the ones you would calculate for the dehydrated protein. Well, that makes perfect sense, because the protein is going to be coated with water. The water is going to slow down the rotational diffusion. So most of the correlation times are longer than you would calculate without hydration. But you'll notice something here is that for almost all of these proteins, especially the larger ones, the correlation times are much longer than most of the fluorophores that we use. And that's a problem, because if it's a 4 nanosecond fluorophore, you're not going to be able to measure the anisotropy over much more than, let's say, 3 times 4 nanoseconds. So it's hard to measure higher molecular weight species from the correlation times in the anisotropy decays, because they basically the probes stop emitting before much rotation has occurred. The first slide on the measurement of anisotropy decays made it look like it was easier than it is. So what do the time resolved data actually look like? As I stated once before, we do not have an anisotropy detector. The only way we can measure an anisotropy is by measuring a difference of intensities. So in the steady state domain, we already showed you how it's done. In the time domain, we look at the anisotropy decays of the parallel component and the perpendicular component for these assumed values here. Total intensity, here is I parallel plus 2I perpendicular. If we look at the individual decays, we notice that the parallel decay seems to decay initially faster than the total decay, and the perpendicular decay decays more slowly than the total decay. The way this can be understood is if you're observing with vertical polarizers, the vertically polarized decay is decaying by two processes, the intrinsic decay of the fluorophore and by rotation out of the plane of observation. So that's why it looks faster. The perpendicular decay looks slower because if you're exciting vertical or you're looking perpendicular, you can't see those molecules until they rotate into the plane of observation. So the decay seems slower. And you use these two data sets to calculate the anisotropy decay. And this is why the anisotropy decays always look noisy, especially at the longer times, because you're always taking the difference of two relatively large numbers. An important thing to notice is that the anisotropy decays are completely independent from the intensity decay. We're sort of lucky that, lifetimes of our fluorophores and the rotational correlation times of the proteins are somewhat similar, but that didn't have to be the case. Nature just gave that to us. But the correlation time is completely independent of the lifetime. This lifetime could have been seconds. It wouldn't have mattered. Correlation time would have been the same. This is one of the, I've always liked this experiment. This is an experiment that demonstrated domain motions in proteins. When this was done, I've forgotten the exact year, it's pretty early. Proteins were sort of viewed as rigid bodies, little rocks that don't really do anything. But over time, people realized that they're probably more flexible than that. So the author here, which I think was Lewis Stryer, took an immunoglobulin and he raised antibodies against danzyl lysine. So we got antibodies specific for danzyl lysines, and they would of course bind to the FAB sites of the antibody. So first, let's look at the anisotropy decay of the whole protein. They're coming together slowly, but it's relatively slow because it's a large protein, and as we indicated here, the rotational correlation time for the IgG is about over 100 nanoseconds. Now, there's the FAB fragments with a little bit of catalytic enzyme like trypsin. You can cleave this apart and get separate FAB units. And when you look at the anisotropy decays of the FAB units with the danzyl lysine and the binding site, you find that the two decays come together much more quickly, meaning the anisotropy decay is more rapid. The calculated anisotropy decays are shown over here. I always like to show the primary data first, but here FAB has a relatively fast correlation time of around 30 nanoseconds, but when we get to the IgG, it's a multi-exponential anisotropy decay, and that's due to the domain motions of the proteins. So the anisotropy decay is due to both flexing of the FAB units relative to the entire protein, but there's also a longer time component, which is due to overall global rotations of the proteins of the IgG. So that's one of the early measurement of domain motions in proteins, and there's been many more since that, these early experiments. I always like this slide because here I try to connect the steady state measurements that you do with the time result measurements. The steady state emission spectra we have here, 3 different intensities. And over here we have the intensity decays for these spectra. And what is usually the case is that the area under the curve of the intensity decay is proportional to the total emission of the fluorophore. That makes sense. If it emits higher amounts over a longer period of time, it should, in the steady state, have a higher intensity. So the linkage in terms of intensities is lower intensities, more rapid intensity decays, higher intensities, slower intensity decays. A similar thing happens with the anisotropies. The steady state anisotropies might be, they're not directly related to one up here. They might be lower or higher, but that's usually reflected in the anisotropy decay. If an anisotropy decay is slower, the steady state anisotropy will be higher. If the anisotropy decay is faster, then the steady state anisotropy will be lower. And that's, of course, related by the integrals over the time of the intensity decay, or the intensity weighted integral of the intensity weighted anisotropies. Okay, here's another biochemical example, which I always like. It's the development of a treatment for AIDS by inhibiting the integrase activity of the virus. In the early studies of HIV, of course, the researchers were looking for any way to inhibit its activity. One way is, of course, you have to convert the RNA to cDNA, so they look for inhibitors of that enzyme, and you have to look for inhibitors of the protease that helps the HIV get into the cells. Finding inhibitors of integrase were more difficult. There are now some small molecule inhibitors of integrase, but one of the first ones that was found, and how they made this connection, I'll never know, but somehow they speculated that the epithelium-derived growth factor, some of their peptides would somehow inhibit the integrase activity. So these peptides are shown here. So they're relatively small peptides, and that could inhibit the integrase, this is a catalytic unit here, its activity by these derived peptides binding to it. And that effect was investigated by looking at the steady state anisotropies. So what they found was that certain fragments, this is the integrase concentration here, certain fragments associated much more strongly, of course higher concentrations to make things associate, in the presence of one peptide, but not in the presence of another peptide. And the data just shown in another formatter here. So this relatively short peptide was found to inhibit the activity of integrase. And since the molecular weight of the anisotropy went higher, it was reasoned that the LEDGF peptides resulted in an aggregation or a tetramerization of the integrase. And that was important because it was known that dimers were needed for the integrase to get the cDNA into the host genome. So just sort of by equilibrium methods, they could pull the equilibrium away from the presence of any dimers. And if there are no dimers around or monomers, then the integration of the host DNA would be inhibited. An important feature of these anisotropy measurements, and I don't know if you've realized this yet, but it does not require the separation of the unbound species and the bound species to get the results. The anisotropy is a weighted sum of the fractions in each form, and you can use those fractions or get them after you correct for any changes in quantum yield. But this is an important feature of anisotropy measurements. They don't require any supports. They don't have to be put on a glass slide. They're often done in microtiter plates because that's very convenient. So that is it for the end of part A. In the next presentation, we'll be describing some more complicated concepts like what is the reason for anisotropy in molecules. Thank you for your attention. Hope we see you next time.